Okay, let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. Dan Keuter, Vice President of Nuclear Business and Development for Entergy Incorporated. Dan began his nuclear career in Portland General's Trojan Nuclear Plant in Oregon after getting his nuclear engineering degree from Oregon State. He is a registered professional engineer, and he's had a senior reactor operator's license for 10 years. He joined Entergy in 1995 as the general manager of the Waterford 3 nuclear plant just west of New Orleans. In February of 2000, Dan was named Vice President of Nuclear Business Development. Since that time, Entergy has doubled its size of nuclear plant fleet by acquiring 5 additional units, $1 billion in new annual revenue, $150 million in annual earnings, 3,500 new employees, and a $250 million payroll in the Northeast. They're headquartered in Jackson, Mississippi. The 5 nuclear plants that Dan helped to purchase in the Northeast provide enough power to serve 4 million people and about 20% of the power demand in the New York City metropolitan area. Prior to joining Entergy, Dan was Vice President of Nuclear Operations Support for TVA, and also he served as the Chief Nuclear Officer for the Sacramento Municipal Utility District's Rancho Seco Nuclear Plant. The title of his presentation today is The Promising Potential of New Nuclear. Ladies and gentlemen, please welcome Mr. Dan Keuter.
Thank you, Lee. Vice President of Business Development, what does that mean? Well, primarily my focus is buying existing plants. We purchased 5 plants in the United States in the last 4 years and doubled our size, and that's my primary focus. But also one of my secondary focuses is actually looking at and evaluating building new nuclear power plants in the United States. And that's what we see as the future, and that's mainly what I'm going to be focused on today is what is the future of nuclear power? What does it look like going forward? Entergy doesn't have a crystal ball. We can't foretell the future, but there's a couple of things that we definitely know for sure about the future. Number one is that there's a finite supply of oil and natural gas, and eventually it's going to be running low, and it is going to get more expensive going forward. The other thing that we know for sure is that environmental regulations are going to get stricter and stricter, and that is how is that going to affect the future? And these two things in mind, we see it's very promising for nuclear power in the future, but also the hydrogen economy. We have to get to a hydrogen economy. We have no choice. It's just a matter of when. Before I get started, though, I'd like to talk a little bit about Entergy. All of you may not be familiar with Entergy, but it is a very large utility, the 4th largest utility in the United States. Its headquarters is based in New Orleans, although the nuclear headquarters is in Jackson, Mississippi. Its service area is Louisiana, Arkansas, Mississippi, and Texas. We generate over 30,000 megawatts. We have over 2.6 million customers. We have revenue of $8 billion a year, and we're one of the lowest environmental emitters in the United States, and our goal is to be the lowest. In the last couple of years, we've won several awards. In 2002, not only did we win the national award for the best utility in the United States, but we won the Global Utility Award and the best in the world. And then last year, one of the awards we had was the Global Energy Award, and this was with not only utilities, but with oil companies, gas companies. So we were voted the best energy company in the world. But one of the things that we're probably the proudest is our environmental record. And this is where Entergy stacks up as far as the top 100 utilities as far as emissions of CO2. You can see we're one of the lowest. NOx, you can see we're one of the lowest. SO2, very low. And then also mercury are extremely low. And we're very proud of this. We want to be the environmental utilities in the United States going forward. As far as nuclear operator, we're the 2nd largest nuclear operator in the United States. We operate all forms of the technology reactors in the United States that are in production in the United States. We're also the fastest growing nuclear operator in the United States. We had 5 units that we had for the last 20 to 25 years. We purchased 5 units in the Northeast. We purchased the first one in 1999. But also we're operating the Keuter plant in Nebraska for another utility that we don't operate. So we're actually operating 11 plants in the United States. Entergy's into nuclear power for the long term. We're very proactive in nuclear power. We're looking at more acquisitions, lease or operates for other utilities, eventually building new plants, but also all forms of nuclear power, including decommissioning, early site permitting, etc. Before I talk about the future, though, I want to talk briefly about what is the present performance of plants in the United States. And the present performance of plants in the United States is nothing short of outstanding. This is a chart of capacity factor over since 1980. And what you've seen in the last few years, the last 10 years, a significant improvement in capacity factor up to where we had the average of all 103 nuclear power plants in 2002 was greater than 90%. And this is outstanding performance, especially considering that every 18 to 24 months, the plant has to shut down and refuel. It takes 30 to 50 days to refuel. And so this is outstanding performance. This improvement in performance in just the last 10 years is equivalent to 23 1,000 megawatt plants in performance in increased capacity. This accounts for about 30% of the demand, increased demand in the United States in the last 10 years. So this is outstanding performance, not only for the Entergy plants, but for all the plants in the United States. But not only operating performance, cost performance has improved. Currently, as you can see in the green line, we are the cheapest form of generation, marginal generation going forward, with the exception of hydro. And this number is around $17 a megawatt hour. Keep this in mind, because I'm going to be referring back to this when we talk a little bit later on. And this is at $17 a megawatt hour, and we have basically no air pollution coming out of these plants. As far as safety, basically the number of NRC significant events that have been reported, as you can see this downtrend, basically to 0.03, essentially zero significant events. Also keep in mind, there's never been a member of the U.S. public that have been injured from nuclear power in the United States. So safety is outstanding. Well, how about worker safety? This chart here shows the number of accidents per 200,000 man-hours, which is about 100 man-years. If you look at U.S. manufacturing, which is the top line here, it's about 4 accidents per 200,000 man-hours. If you look at nuclear power, right now, this is 2000, 0.26. So it's 15 times safer to work in a nuclear power plant than it is in the U.S. manufacturing in the United States. What's really interesting about this chart, though, is if you look at office workers, which is this red line here, it's 0.7. So it's 3 times safer to work in a nuclear power plant than it is in an office space in the United States. Why is this happening? Why have we had this significant improvement in nuclear power? Nuclear power is a maturing industry. When we started off in the early 70s, it was a new industry. We've learned a lot. We've implemented IMPO, and we've had technology breakthroughs going through. But probably one of the main reasons is we've had a consolidation of the industry. If you look at the total number of plants, which is the blue bar here, it's basically we still have the same number of plants. But if you look at the number of operators that operate the plants, it's gone from 54 10 years ago to 27 today. So we have basically the same number of plants being operated by half as many people. So we've had a consolidation. We have large nuclear operating companies that specialize in operating nuclear power. The other thing to look at, the number of people that operate just one unit. 10 years ago, there's 27, so half the plants were operated by just one utility operating one plant. If you look at where it is today, we're at 8. The other thing is, what is the future? There's going to be a continuing consolidation of the industry to the point, probably in another 10 years, we're going to be less than 10 major operators in the United States. So you're going to see a continuing consolidation, which I think is going to be good for the industry. How about other forms of generation? This is an interesting chart. What it shows is what kinds of new generation have been built in the United States over the last 50 years. And what you saw is, the energy crisis in the mid-70s. We had a lot of increased generation come online. We basically got into an overbuild situation. We had lots of nuclear come in the 70s, mid-80s. But what you see here in the last few years is a huge amount of natural gas generation. It was very, very hard to compete with natural gas when natural gas was at $2 a million BTU. Well, natural gas, all of a sudden what's happened is we had this huge increase in demand of natural gas. At the same time, we've had a decreasing supply of natural gas in the United States. So what has happened, prices have gone all through the 90s, we're in the $2 per million BTU range. Now they're more than doubled or tripled. They're up to $5, $6 a million BTU. And keep in mind, if you have a 7,000 heat rate for a natural gas plant, which is new plants are doing, if you just multiply 5 times 7,000, you have $35 a megawatt hour just to pay for the natural gas. Keep in mind that earlier chart when I said nuclear power is operating today at marginal cost of 17. So what you've seen is a huge overbuild in natural gas plants. We put all of our eggs in the natural gas basket, and all of a sudden that natural gas basket has developed a big hole in it. The other advantage of nuclear power is its non-emitting generation. Keep in mind, I said one of the things we know for sure about the future is that environmental regulations are going to get stricter and stricter. So what do these environmental regulations look like? These are the three major bills out there. We got the Jeffers bill, which is supported by the Democratic half of the legislation. You have the Clear Skies, which is supported by the administration. You also have a Keuter bill, which is being supported by a lot of the utilities in the United States, which is kind of a compromise between the two. Those are the three major proposed regulations out there. There's subcategories of each of those. And when you look at the primary air emissions, you got SOx, NOx, mercury, and CO2. And other than CO2, you see that the amount of reductions is about the same. It's just a matter of how fast you implement them, with the exception of CO2. In CO2, the Jeffers bill, you have very aggressive, getting down to 1990 levels of CO2 by 2007. The administration is relying on voluntary cuts. And then the Keuter bill, which is supported by a large number of utilities, has CO2 restrictions, but it's in a longer time frame. So the main difference between them is they're all about the same with the exception of CO2, and we feel that CO2 is coming. It may not happen in this administration, but it's definitely coming. This is a look at U.S. emissions by sector. Again, it uses NOx, SOx, CO2, and what you see here is a continuing decrease of emissions for utilities, which are the blue lines, in both NOx, SOx. CO2 basically stays the same under the current programs, but what you see is it's about 1/3 energy sector, 1/3 industrial and residential. If you add residential onto industrial, they're all about the same. And then 1/3 for transportation. In the long run, what you see is transportation is going to be becoming this dominant CO2 emitter. The bottom line here is you can regulate utilities to a point, but after that point, it's going to take all sectors to participate to have any other additional significant reduction. You can't just regulate down electric utilities and hope that you're going to get to the goals you eventually want to get to. Remember I talked about CO2. I could sit here and talk for probably another 2 hours just on CO2 and greenhouse gases, which is the intent of today, but it is coming. And what you see here, this is the United States is by far the largest emitter of CO2 in the world. In fact, if you add the next 6 together, it's still less than what the U.S. So the U.S., I think, is going to have increasing pressure worldwide to reduce its amount of CO2 going forward. So we feel it may not be here now but it is coming. So what should environmental regulation do? What should it look like? What are we proposing? I think the conclusion coming out of here is definitely a cap and trade system is the most economical thing going forward, where you put a cap on it. If you have allowances, you can trade them, sell them to others. You have an open market for allowances. We definitely think it should include all four pollutants, including CO2. The other thing is we think it should be a fair allocation for all generations. Right now, under a lot of existing, like SO2, what they do is they grandfather some of the existing generation, give those polluters the allowances, and in the end run, what you're doing when you do that is, this is called input-based allowances, is you're rewarding the people that are polluting by giving them the free allowances. You don't give any allowances to the non-polluters, so you're putting them at a detriment. So going forward, we want to make sure all generation is treated the same. You can give allowances out. If you do it, let's put it on how much generation you put out. Give it to the non-polluters, and then they can trade it to the polluters at market prices. Or basically, you just go to an auction. You treat allowances just like you do natural resources, just like radio frequencies or forest land or oil rights or gas rights. You just go out, and if you want to pollute, you have to go out and buy those allowances from the government, and it's on $1 per pound. So what this does is it opens up a free market. And the other thing is we think we should do this for all sectors. Remember this, we can't get to where we want to just relying on utilities. But if a lot of people are against this, they say, well, this is a carbon tax, or this is a pollution tax. You're exactly right. That's exactly what it is. You're taxing the things you want to reduce. If you stop and think about the way the taxation is in the United States, the two things that you really want to increase in the United States is labor and investment. So what two things do we tax the heaviest? Labor, income tax, and investment tax. The one thing that we're trying to decrease in the United States, which is pollution, we don't tax at all. In fact, right now we give free allowances to polluters because they're polluting. So we think going forward, these are the major things that new legislation should have. Well, how about renewables? Entergy's all for renewables. We think it's a great thing going forward, but we do have to keep it in perspective. I call this my pigs and chickens slide. Basically, if you look at the different forms of renewable generation, and if you say this is equivalent to a 1,000 megawatt electrical plant operating basically at 90% for the year, how much area or square miles would you have to have the equivalent amount of generation? Photovoltaic, you'd have to have 40 square miles. Wind, you'd have to have 40 to 70 square miles. If you get into biogas, you'd have to have 60 million pigs or 800 million chickens to produce the equivalent amount of a 1,000 megawatt plant. That's a lot of pigs and chickens, even in Arkansas. Bioalcohol, now you're talking thousands of square miles. Bio oil, thousands of square miles. Biomass, the same. You talk about a nuclear power plant, you're talking about a third of a square mile. We think renewables are good. There is a place for them in the future. Right now, they're not economical, but we need to get there eventually. So what is it going to take to build a new nuclear power plant in the United States? Now, keep in mind, there are 23 plants in development worldwide. So the real issue is how do we get there in the United States? Because other countries are building them. I think the first place you got to start is right here at the top, and we have to have a national energy policy. The policy has to address energy supply and security, environmental policy, fuel diversity, economic price anchors. We were very enthusiastic what came out of the energy bill. It didn't pass. Eventually it will pass, and we're optimistic about that. So we think that's underway. The next thing you need is regulatory certainty. That's underway too. 10 CFR Part 52 is addressing the regulatory certainty. It's addressing early site permitting, design certification, combined construction operating license. So again, we feel that's underway. You have to have safe economical designs going forward. There's several designs out there that are certified. Unfortunately, right now, we don't feel those are economical in the United States, but there are other potential designs out there, including the Westinghouse AP1000, which we think is very promising, the GE EFBWR, which we think is very promising, but also the Canadian design HDR700. In the future, beyond advanced light water reactors, we see very potential promise for gas reactors, including the pebble bed and the prismatic designs. So again, we think that this is making progress. Coming around to the other side, we have to address risk mitigation and financing. We have to get through the first few plants, the first-of-a-kind cost, address the first-of-a-kind cost, the first-of-a-kind risk. This includes first-of-a-kind, the cost, the high capital, the regulatory certainty, earnings dilution, and market price. Again, the energy bill had several things in there, including potential production tax credits, government loans, cost sharing of first-of-a-kind design. So we think that has been in making progress. Then you have to come down to the individual plant economics. You have to make sure that they make sense going forward, not only for the first-of-a-kind plants, but nth-of-a-kind. But the bottom line here is it's going to be Wall Street that determines when we start building new nuclear power plants in the United States. With that in mind, they're not going to start giving you basically financing until you validate the design, the construction, the regulatory process, operations, and financials. So what we need is government support to help us build the first few plants. Once we validate through these demonstration plants, then we do see that we will start building plants in the United States. Entergy is actually going to a true track approach. We're actually going down, looking at the economics, advanced light water reactors. It's a mature technology, increases field diversity in the short term in the United States, and reduces not only air pollution, but greenhouse gases. We're going down a second track also. We really like the gas technology. We think it's going to be economical. It has the potential to produce not only electricity, but hydrogen. It has very good safety characteristics, which we like. And I'll be talking a little bit more about this at the end. One of the things the anti-community is saying is, well, nuclear power is already over-subsidized, and nothing could be farther from the truth. If you really look at this chart here, is you look at the amount of R&D that has been invested in the last 10 years, compare nuclear to fossil, energy efficiency, solar renewables, and fusion, you can see that it's pale when compared to those. The other thing to keep in mind is that the nuclear industry is the only one that pays 100% of its environmental impact. We're the only industry, instead of not paying for pollution, we are collecting $1 per megawatt hour to dispose of high-level waste. We're the only industry that pays for our environmental impact. We're the only industry that pays 100% of our regulatory costs. We pay 100% of the cost of the NRC to regulate it. We're the only industry that does that. We're the only industry that prepays decommissioning costs in advance. We're the only industry that pays for its accident insurance itself. So when people say that the nuclear industry is being subsidized, nothing could be farther from the truth. In fact, it's probably the least subsidized industry in the country. Long term, what happens in the long term, we think that once we get through those first plants, demonstrate, validate it, that we won't need any subsidies after that we will be able to get conventional debt service from Wall Street. We would like to continue with a 7-year accelerated depreciation. Right now, pulp and paper plants can accelerate depreciation over 7 years, and coal plants, other plants can't. We can't. We have to do it over 15 years. We can get long-term PPAs with our distribution company. We'll get down to the cost where instead of the first-of-a-kind cost, we'll be down to nth-of-a-kind or multi-plant. And eventually, we're going to get recognized, we feel, for the environmental value of being a non-emitter. So what is the value of not emitting pollution in the United States? What this chart shows here If you would have shut down the 103 nuclear power plants in 2002 and replaced that power with existing generation, meaning mainly coal, oil, natural gas, whatever is in there, basically, and then look at the amount of SOx, NOx, mercury, and CO2 that comes out, the increase in tons from that, the mercury, which isn't being traded now, we assume $2 a megawatt hour, times the price that it's actually being traded at in Chicago, and this was last year's numbers, and multiply this out, basically what you're coming up with is the value for each of these. This is equivalent to $10 billion in 1 year alone. This is $10 billion in avoided cost of pollution from nuclear power for 1 year. If you divide that by the 103 nuclear power plants, that's equivalent to $100 million per plant per year. If you multiply that out and put it in dollars per megawatt hour, that's about $12 a megawatt hour. That's a huge number. If you turn around and NPV that back, that's about $750 per kV. So if a new plant costs $1,500 a kW, this will pay for half the cost. So these are very big numbers. That was my back of the envelope calculation. Last year, EPRI came out and did a very detailed evaluation. It was interesting that their numbers came out very close. They did theirs for all non-emitting generation, including nuclear, wind, solar, biomass, and they went through and said, okay, if you took the value of NOx reductions, SOx, mercury, CO2, and basically it came out to about $90 per kilowatt year. If you turn that back into a present value, that's, again, about $750 a kW. So you're paying 50%, or potentially paying 50% of the cost of the initial plant just from its environmental value. If you turn around, multiply that 90 times 1,000 kW per megawatt, years per year, 85% capacity factor, again, it comes out to about $12 a megawatt hour. Very large number in potential value that isn't being recognized today for nuclear power. One of the questions that comes out was why is there a difference for other non-emitters? Why is nuclear power more valuable? And the reason is nuclear power plants operate about 90% capacity factor. If you look at wind, it's only about 30% capacity factor, and solar is even less than that. So you have a much bigger value because of the increased capacity factors of nuclear power. How about high-level waste? Again, this is something the anti-community is putting out there. They're saying there's no solution for high-level waste. Well, absolutely untrue. There is a solution for high-level waste. It's deep repository burial of high-level waste. What's being proposed is Yucca Mountain. And let's keep it in perspective. The total amount, if you took the 100 and so nuclear power plants in the United States, operated them for 40 years, the volume of rad waste that we would have, that, trust me, UT would get this analogy, would cover a football field about 5 yards deep. So it's manageable. This doesn't take into account that eventually I think we're going to get into recycling and taking the long-lived isotopes, put them back into the reactor, take the usable uranium and plutonium out, put them back into the reactor. Other countries are doing that today, including the UK, France, Japan, and Russia recycling waste. So again, this is manageable. There is a solution. It's just that the anti-community doesn't want to admit it. In conclusion, as far as what is it going to take to build nuclear power plants in the United States, for first-of-a-kind plants, we're going to have some support from the government. That could be loan guarantees. It could be production tax credits. But we are going to need some help to get through those first-of-a-kind costs and risks. We need debt financing and risk insurance. We need to get the capital costs for the first-of-a-kind plants at less than $1,600 a kW, which I think we're already there, and long-term purchase power agreements, which we think we're there. In the long run, what we need is to recognize the environmental value of nuclear power. If we can do a demonstration plant, we will get debt financing from Wall Street. Into the kind plants, we think we can get the cost down. $1,000 per kW for dual units, $1,250 for single units, so they can be competitive. We will be able to get long-term purchase power agreements. They're even more economical when you have dual units, and we need the economics of passively safe plants, and there's several that are in design today. A lot of you may have heard about the MIT study. Basically, MIT put out a fairly detailed study on the future economics of nuclear power plants. And what was the conclusion out of that study? The basic conclusion is that if you use very pessimistic numbers and put it into the model, nuclear power isn't competitive. In fact, the assumptions they originally used that says that nuclear power is at $67 a megawatt hour. Very expensive. And compared to other forms of generation, including coal and natural gas, was not competitive. Now let's use realistic assumptions. If you use realistic assumptions in the same model, it paints a totally different story. If you reduce the construction cost by 25%, they assumed $2,000 per kW. Well, we're getting firm offers today from vendors to build it at $1,500. So if you reduce it down to realistic numbers of $1,500, now you're down to $55. Reduce construction times. They assume 5 years to build a single unit. Well, plants are being built overseas in 4 years. So if you use 4 years, you're down to 53. Reduce O&M. They assume something higher. I think it was $15 a megawatt hour. If you assume 13, which plants are operating at today, new plants should be even cheaper. So if you use a realistic number for O&M, you're down to 51. The other thing they assumed is debt financing or cost of capital for a nuclear power plant was 15%. Well, they assumed 12% for coal. Again, I'm assuming this is an nth-of-a-kind plant, that you've already proved that you can do it, that you can control the risk. But if you use 12%, the same as what they were using for coal, now you're down to 42. The other thing is they use an 85% capacity factor. Well, plants today are operating at greater than 90%. So if you take that into account, you're basically down to $40 a megawatt hour. $40 a megawatt hour is very competitive with everything but very low natural gas. Well, very low natural gas isn't here. I mean, it's $2 or $3 a million BTUs. They assumed $3.77 average over the next 20 years. It just isn't going to get that low again. So it's very competitive with existing generation if you use realistic assumptions. Well, if you turn around and then say, well, how does it compare if you use some kind of carbon restrictions going forward? And what this shows, these are the same numbers from the previous slide. You got nuclear at 40, 42, I assume here. You're very competitive, but if you even assume even a minimal amount of carbon restrictions or carbon tax, nuclear power becomes very, very competitive. And people talk about coal sequestration. When you talk about sequestration, now you're talking about potential costs in $200 per ton of carbon. And then you're very, very competitive going forward. So the bottom line on the MIT study is, garbage in is garbage out, but if you use realistic numbers going in, numbers that are already being, validated today, and you assume an nth-of-a-kind plant, nuclear power is very competitive, and if you assume any kind of carbon restrictions, it's very competitive. Next, I'd like to talk about the reactor of the future, and it's a gas reactor. We think this is the reactor of the future, and we call it a freedom reactor because it can produce not only electricity, but it can produce significant amounts of hydrogen pollution-free, and we think this is the technology of the future. So what does this freedom reactor look like? It's a new, simple design. It's very safe, very economical. It's a modular reactor. Basically, it's a 288 megawatt electric. For one site, you put 4 of them together, operate by a common control room. It's modular, so it's a simple design. A lot of it is factory built. One of the concerns nowadays is about terrorism. This is ground level right here. It's extremely hard to hit a reactor that's underground with an airplane. So it's very terrorist hardened, very it's below grade. It's low cost, has low construction time. The first unit would be less than 3 years to build the first one, and you could potentially put another unit on every 6 months to a year after that. Capital costs, we're looking at in the range of $1,000 per kW for nth-of-a-kind plants. O&M, fuel and O&M, $10 a megawatt hour, and low decommissioning costs. Basically, as far as decommissioning, you got the reactor vessel here to dispose of. You also have a power production unit here to dispose of. You seal them up, you bury them as one piece, so you can have significantly reduced decommissioning costs. It's proven technology. This reactor has 40 years of experience in gas technology. It's the same core design as what was used at Fort St. Vrain. It does use a Brayton cycle versus a steam cycle, so you have very high efficiencies in the range of 50%. And it uses helium instead of water, which is inert, non-corrosive, and doesn't absorb neutrons and it doesn't become radioactive. One of the things that makes this significant, it does use a gas cycle versus a steam cycle, so you have significantly less equipment. Not only do you not have all the steam cycle heaters, condensers, you still have a generator, but all the support balance of plant isn't there on this technology. The other thing is it uses passive safety, so you don't have active safety systems to build and maintain and operate in the future. So the real thing, as far as economics, is having significantly less equipment in this design. So it's also extremely safe. We say it's meltdown proof. You have multiple ways of getting rid of decay heat. The primary way is just to motor the generator, continue running the compressor to remove decay heat through whatever your tertiary heat removal system is, a cooling tower. You do have an active safety system at the bottom of the reactor. It removes heat through a radiator system. It does have a passive safety system, which just has natural circulation, rotates air through natural circulation through the sides of the silo and can remove heat. But even if that fails, even if this is knocked out, just dissipating heat to the ground, you'll never get hot enough to melt the fuel. So no matter what happens, the fuel isn't going to melt, and therefore it's meltdown proof. So it's a significant improvement in safety. The last thing I'd like to talk about today is hydrogen and the hydrogen economy and nuclear power teaming up with hydrogen to get to this hydrogen economy. Remember two things I said at the beginning is the two things we know about the future is there's a finite amount of natural gas and oil, and air emissions are going to get stricter and stricter. So therefore, we feel we eventually have to get to a hydrogen economy in the future. And what part can nuclear power play in getting to a hydrogen economy? The advantages of hydrogen, so why do we have to transition to a hydrogen economy, is reduced emissions. We have no NOx, no CO2 for transportation. So we have a significant reduction in air pollution. Reduced dependency on foreign oil and gas. Like I said, eventually we're going to run out. We have to get there. We're extremely reliant on foreign oil today. We will become reliant on foreign natural gas in the future as we deplete the natural gas in the United States. So there's an advantage to getting to hydrogen. It can be a renewable's best friend. One of the shortcomings of renewables is usually they're far away from where you use it, and two, electricity isn't storable. Now hydrogen you can't just drill into the ground and produce hydrogen. It's like electricity. It has to be produced from another energy source. Even though hydrogen is the most abundant element in the world, it doesn't stand by itself. You have to produce it. But hydrogen economy only makes sense if you can produce it cheaply, economically, and not emitting. You have to be able to do that, or it doesn't make sense. It doesn't make sense to get to a hydrogen economy if you're going to use natural gas to produce, the hydrogen in the first place. Currently, 95% of the hydrogen produced in the United States is from natural gas, so it doesn't make sense to use natural gas to produce hydrogen when it could have used natural gas in transportation in the first place. So what is the existing demand for hydrogen today? There is actually a hydrogen economy today. In fact, one of the reasons that Entergy is so interested in hydrogen is approximately 70-75% of the hydrogen that is produced and used is in our service areas today. And it's mainly used in three areas: oil refinery, to make ammonia, to make fertilizers, and then industrial uses. Demand with natural gas prices going up, keep in mind I said 95% of it is produced with natural gas. With natural gas prices going up to $5 and $6, a lot of the ammonia production has moved overseas. We've lost those jobs. We lost that in the economy of the United States. They're going over to where natural gas is cheaper. For the future demand for hydrogen in the near future, within the next 10 years, is for the production of gasoline. Texas sweet crude didn't require any hydrogen to be added to make gasoline. Venezuelan crude and foreign crude coming in is short of hydrogen, so they have to inject hydrogen in it to get it. In fact, with more reliance on foreign oil now, they predict that in the next 10 years, there's going to be a quadrupling demand for hydrogen for refineries. We do see it as a bridge to the hydrogen economy. We do see that transportation, in fact, BMW is making hydrogen combustion engines today as a solution, but also future fuel cell technologies. Fuel cells, they basically are twice as efficient as a combustion engine. So even though it might be more costly to produce hydrogen than gasoline, if you use it in a fuel cell, it's going to be you get twice the miles out of it. One of the EPRI studies that they completed last year was an economic study on the production of hydrogen. What are the cheapest ways of doing it, the most economical? They looked at several different methods: electrolysis, natural gas reformation. They also looked at high-temperature gas reactors. And basically what came out of that study is you could produce hydrogen at about $1.50 a kg. And a kg is about equivalent to a gallon of gasoline. Now, if you use that hydrogen in a fuel cell and it's twice as efficient, basically you get twice as many miles out of the same gallon of gasoline or the same kg. So that brings it down to 70% or 75 cents equivalent gallon of gasoline. The other thing is it produces oxygen. You can sell that oxygen. So it does have a usable byproduct that you're going to get some value. But forecast demand, we see the forecast for hydrogen being 18 times current demand. And when we get to a hydrogen economy, it's going to be 40 times. We do see that the demand for hydrogen is probably going to exceed demand for electricity in the future. The DOE goal is to get to 10% of transportation by the year 2030. That was a test to see if anybody would catch it. But the demand for current demand for hydrogen is very high, and it's going to get higher in the future. Getting hydrogen from nuclear. So how do we do that? So why does this make sense? Well, you could do it today. In fact, you could use electrolysis today. But the problem with electrolysis is you have to make electricity in the first place. Electricity out of an existing nuclear power plant is about 33% efficient. Electrolysis is about 80% efficient. You multiply that together, you have an efficiency of only 25%. If you use a high-temperature gas reactor, which is about 50%, multiply that by 80%, then you can get up to 40% efficiency. It could be an intermediate step. One of the nice parts about low-temperature electrolysis is you can transmit the electricity in the middle of the night to service stations, and there is no restriction on transmission at night. You have a surplus of power, you have a surplus of transmission, and then you can produce it through electrolysis at individual service stations to supply the car. So there is some advantages to it in the total infrastructure, but the total efficiency isn't there. There's a thing called high temperature electrolysis, where you basically preheat the water, in this case the steam, up to extremely high temperatures. Therefore, you don't need as much electricity to produce it, and you can get up to 50% efficiency in high temperature electrolysis. And that's one of the things being evaluated today by EPRI and the DOE. Thermochemical splitting of water, basically, there's different chemical processes. One of the ones that we like is the sulfur iodide process. Sulfur and iodine acts sort of like a catalyst, not a true catalyst. But using this process, you can get up to efficiencies of 50 to 60%. Like I said earlier, you can also produce the oxygen for resale. It's a very low cost. You can use maybe some of the byproduct heat for desalination. But the problem with both high temperature electrolysis and thermochemical splitting is you need extremely high temperatures. You need temperatures in the 900 degrees centigrade range. And the reactors out there that have that capability right now are, again, gas-cooled reactors. So the Freedom reactor, which we talked about, has that capability, and we think is another good reason for developing that technology. One of the things that was proposed in the energy bill and still out there is to demonstrate a Freedom reactor or high-temperature gas reactor at Idaho. Basically, this is a pictorial of what that might do. You have your high-temperature gas reactor here that's producing electricity and heat. You can take some of the heat off to a thermochemical splitting plant, or take it off, use some of the electricity heat to go to a high-temperature electrolysis plant, and demonstrate the use of high-temperature gas reactors for the production of electricity and hydrogen. This program is very similar, and it's called Next Generation Nuclear Reactor. It's very similar to a program that's already been implemented by the DOE called FutureGen. FutureGen is basically the equivalent to demonstrate using clean coal technology to produce electricity and hydrogen. But one of the main things on FutureGen is sequestration. Sequestration is basically taking the carbon out of the CO2 and then sequestering it, basically burying it underground or putting it in some other place and leaving it there forever. That sounds good until you start really thinking about some of the numbers. So basically, a large coal plant burns about 1,000 or 100 train car loads of coal a day. That 100 train car loads of coal actually, on weight, produces 340 train car loads of CO2. So now you're going to take this CO2, bury it underground, and hope it stays there forever, because it doesn't decay off. Now, what is the problem? What happens if it leaks up to the surface? Not only does it create greenhouse gases, but CO2 also is heavier than air, so it lays on the ground. Well, what happens? Well, one of the things that happened is there was an incident in Africa in the mid-'80s where they had a lake that got saturated with CO2. It burped, put out a lot of CO2, and killed everything. Not only every person, but every animal within a 5-mile square radius of that lake. So sequestration might sound really good, and they're saying they're doing it today. They're pumping it down oil wells today. But when you look at the total volume and the problems if it ever leaks out, it isn't as simple anymore. But again, this is equivalent to the FutureGen. I'd like to close and just say, well, where's public opinion going? And there's been a lot of studies came out, and you can see after the California crisis, we hit an all-time high as far as public opinion. Post 9/11, it went down, come back up to the blackout, it's going back up. But what is the rest of the story? Well, when they ask these people, they also ask them, well, okay, you support nuclear power. Well, what does your neighbor think? Most of the people think that they support it, but their neighbor doesn't, which doesn't make sense. The other thing is, a lot of the public thinks that nuclear power causes pollution, air pollution. And when they find out it doesn't, the public opinion goes up almost 20%, goes up close to 80%. So again, I think that going forward, nuclear power has go out and has a PR battle, or has to be out and educate people on what are the positive parts of nuclear power going forward. With that, I'd just like to conclude and ask if there's any questions.
Okay. Hey, Dan, we'll take questions. Have any questions? Jack?
Run through Wall Street's opposition with me once again. If you wanted to implement a freedom reactor or something like that, I could understand their concern as a new technology. There, I need some government guarantees. But the technology that you could use today is not all that different than the technologies that we have existing currently. So what is the opposition to going without government support?
Well, one of the things you need to do is get 50-50 debt to finance. So you need basically financing, 50% debt financing to make the numbers work, the numbers I showed up here. And I think Wall Street right now is very comfortable with existing plants. If the plant is up, built, operating, they're very comfortable with it. Wall Street has been very, happy with the performance of the plants that we bought. That they're operating, they're, making good money. Their concern is there's the risk and uncertainty of building a plant, one, within the time frame you're proposing, 4 to 5 years, and two, at the cost of what you think. And Wall Street has a long memory. They remember the cost overruns of the past, and they're still concerned about that. Now, the only way I think we can convince Wall Street is to actually do it. Do it in the United States. Prove the regulatory process, prove the construction schedule, prove the construction cost, and prove the operating cost. Once we do that, I think Wall Street will be very, very supportive. Until then, they're just going to be skeptical and concerned. This is a lot of money. This is a lot of money for one utility, even Entergy, step out and build a $2 billion plant when our total capitalization may be $10 billion. So until we get there, and it's going to be, I think, multiple utilities going forward with government support for the first-of-kind costs and risk to get there. And after that, I think nuclear power is going to be supported not only by Wall Street, but by everybody else. Other question?
To follow up on Jack's question, we just had lunch with Dan, and he commented that as a result of buying the 5 new nuclear power plants, that the stock in his company is at an all-time high. And there's another utility in the southeast, not to mention any names, who's invested heavily in natural gas, and their stock is at an all-time low. So the market economy, that says something.
But I think the economics will prove out. It's already been a good strategy for Entergy. Like we said, our stock hit $60 a share last week or the week before last. When we started our nuclear growth strategy, 5 years ago, it was at an all-time. It was like $15 to $20. So it's the economics and the strategy for us has been very positive. Now there's other things that we have done or not done. We didn't invest heavily in natural gas like other utilities, but we haven't made some of the mistakes of trading electricity and natural gas that other utilities or other companies have. So it's not totally new nuclear power, but nuclear power investment in these 5 plants has had a large share.
Are there any poll figures for the United States available that will indicate what fraction of the adult population thinks that a nuclear reactor is like a fission pond? I know for foreign countries there are figures like that.
There probably are. I don't. If you contact NEI, they might have that. I don't. But there's a concern. People think of nuclear. They think of nuclear bombs. They think it's going to blow up. They don't realize that nobody in the United States has ever been injured from, member of the public injured from nuclear power. And so that they remember the negative things, but they don't realize the positive things like being non-polluting, being an energy source in the United States, getting off of foreign oil, foreign energy supplies.
When do you think there will be a new start?
This is the same question they asked me at lunch. one of the recent developments is the DOE came out with a solicitation, I think in November, to do a cost sharing for a combined construction operating license. Last November, it's going to be open till this December. You might see some people responding to that. I don't think it's going to be responding to build a plant, but it'll take the next step. There's 3 utilities already participating in early site permitting, of which Entergy's one. I think the next step is to go through a combined operating license, construction operating license, and then eventually I think there'll be orders for new nuclear power plants by somebody, if not multiple people, by the end of the decade. But it's a stepwise process that we got to go through. But some of the first things we got to get through is energy bill. To help us get through those first of a kind costs. Some people ask me if the energy not passing that as a showstopper. I said not immediately. Eventually we will need government loan guarantees or production tax credits to get the first few plants built, but we don't need those today. So we need to develop the designs. We need to get those going, get that combined operating license, need some co-funding from the government on that, and that's the first step we're going to get through. And that's
Okay. As usual, I see a few new faces in the audience. We not realize that we have a reception immediately presentation that's downstairs on the second, and let's express our appreciation to Dan again for his excellent presentation.